Good day once again. Now that we have explored the structure of the IDF and its essential elements, we move now to the third part of this video, which focuses on the science education framework, specifically its pedagogical theories, approaches, and its connection with the IDF. So as you watch, think about how this can guide your science teaching practice and specifically in teaching science in grade 6 or in grade 9 or in grade 10.
Now, we move from the general framework of instruction to the science education framework, which helps our teachers understand the specific principles, approaches, and ways of thinking that should shape effective science teaching and learning. We have seen how the instructional design framework provides the overall structure of planning instruction. The next question is this: if the IDF provides the structure for designing instruction, what pedagogical foundations should guide how science is taught? And to answer this question, we will focus now on the pedagogical aspects within the science education framework. So you are seeing now in the slide the science education framework. While the instructional design framework gives us the general structure for planning instruction, the science education framework helps us understand the specific pedagogical and disciplinary foundations of science, teaching, and learning. It shows how science should be taught as a way of thinking, investigating, and applying ideas, not just simple memorizing facts, while developing the inquiry skills and responsible, meaningful engagement with the real world. As we look more closely at the science education framework, we can see that science teaching is supported by two important layers. At the foundation are the educational foundation or educational pedagogical theories or models for science. And these give us the theoretical basis on how learners learn best. And from these foundations come the pedagogical approaches for science. And these are the more classroom level ways of teaching that we actually use in planning and delivery, such as inquiry based, transdisciplinary, problem based, or the science technology society, and application led approach. So that we have seen now the science education framework, the next question is, how do we bring all of this into actual classroom practice? And this is where the instructional design framework becomes important. It serves as the bridge between what science curriculum intends learners to achieve and how teachers can implement those intentions. Thus, science education framework defines the desired learning, while the IDF translate it into structured, learner-centered, and aligned teaching. Then, as we go deeper into the science framework, we also look at the pedagogical theories and models that support how learners learn, as I've said earlier. Included here are again the constructivism and experiential learning, social cognition, brain based learning, and Vygotsky's zone of proximal development. Note that the learning style theory in red appeared in the previous framework, but it was removed in the revised curriculum because it lacks sufficient empirical evidence as basis for instruction. So this slide now presents two important foundations in science teaching, which are the constructivism and experiential learning, and as well the social cognitive learning model. So the constructivism and experiential learning emphasize that learners actively build understanding through experience, inquiry, and real life application, such as, let's say, investigating phenomena, testing ideas, and solving problems. Meanwhile, the social cognitive model highlights that learning also occur through observation and interaction, making discussion, demonstration, collaboration, and guided practice essential in science classroom. Here, the two other key foundations are the brain based learning and the zone of proximal development. Brain based learning emphasizes aligning teaching with how the brain learns through connection, repetition, meaningful experiences, and multisensory engagement, while recognizing that emotion and errors are also part of learning. ZPD focuses on the gap between the learners can do independently and with support, highlighting the role of scaffolding to gradually develop independence. Now let us move to the pedagogical approaches for science. So if the pedagogical theories and models explain how learners learn, the pedagogical approaches help guide how instruction is planned, delivered, and assessed in the classroom. So in the science framework, several key approaches are emphasized. So these are the inquiry-based approach, which develops the questioning and investigation, the transdisciplinary approach, which connects science with other disciplines, the science technology society or the contextual approach, which situates the learning in real life issues and applications, the problem based or the design based learning, which engages learners in solving authentic challenges, and the application led approach, which highlights the use of scientific knowledge in practical situations. But before we discuss these approaches, it is also important to understand the hierarchy of pedagogical instruction. So here, theory explains how learning happens. That approach provides the overall direction. Method gives the structured way of implementing it, and strategy refers to the specific classroom techniques. So, in short, theory guides understanding, approach sets the direction, method organizes implementation, and strategy defines what teachers actually do in the classroom. Now, let us take a look more closely at the first three important pedagogical approaches in science teaching: the inquiry based approach, transdisciplinary approach, and the science technology society approach. So let's have first the inquiry based approach. And this approach views learning science as a process of asking questions, investigating, gathering evidence, and forming explanation. So instead of simply giving answers, the teacher creates opportunities for learners to explore concepts actively. And this is why inquiry based teaching often involves guided investigations, hands on experiments, and problem solving tasks. So, for example, in a lesson on plant growth, so the teacher may ask, do plants grow better in sunlight or in shade? So rather than give immediately the answer, the learners set up simple investigations, observe some changes for several days, record their data, and draw conclusions based on the evidence. And the goal is not only to learn scientific facts, but also to develop scientific thinking and habits of inquiry. Second is the transdisciplinary approach, and this approach goes beyond teaching concepts in isolation by integrating science with other disciplines and real life concerns. And also, it also helps learners see that many issues in real world do not belong to just one subject area. So, for example, a lesson in waste management that we may combine science concepts on biodegradability, then mathematics in organizing survey, then also have language in writing persuasive campaign slogans, and then araling panlipunan in discussing community responsibility. And through this approach, learners develop a more holistic understanding and learn to work across ideas and contexts. Third is the Science Technology Society approach. And this approach highlights the relationship between the science, technology, and the society. It helps our learners examine how scientific knowledge and technological advancements affect people's lives, communities, and the environment. It also encourages our learners to think about the social relevance of science, including, let's say, ethical issues, responsible use of technology, and decision making in real world situations. So, for instance, a lesson in plastic pollution. So the learner may examine how plastic products make our daily life convenient, but also how improper disposal harms ecosystem and our communities. So they may discuss the possible solution, such as reducing single use of plastics, improving the waste segregation, or supporting community recycling efforts. And in this way, science becomes more meaningful because the learners see its direct connection to society. Next, the last two approaches in teaching science is the problem-based or the design-based learning, and as well as the application-led approach. So in the problem-based or the design-based approach, it starts usually with a real-world problem or a challenge or a design task that learners need to investigate and respond to. So in problem-based learning, learners analyze authentic situations, ask questions, gather information, and propose solution. The emphasis is always on the output or the result of solving the problem. That is identifying a sound and evidence-based solution to a given issue. In design based learning, which is closely linked to design thinking, learners go through a step further by creating, testing, and improving a product or model or a solution. So here, the focus is not only on the final solution, but on the process that learners go through. So let's say understanding the problem, generating ideas, prototyping, testing, revising, and improving. So, for example, a science in class on heat and insulation. So, learners may be challenged to design a container that keeps water warm for the longest time. So, in problem based version, the learners may study the problem and recommend the best insulating material. In the design-based version, they actually build a prototype, test it, revise it, and improve the design based on evidence. And in both cases, learners apply scientific concepts, work collaboratively, and engage in meaningful problem solving. Then the last approach is the application led approach. And this approach begins with the idea that science is best understood when the learners see how it is being used in real life situations. So instead of stopping at the concepts and theories, this approach emphasizes the practical application. So the learners use what they know in meaningful contexts, connect classroom learning with everyday life, and develop skills that may prepare them for the future studies. So for example, lesson on mixtures and solutions. So learners may apply their understanding by preparing an oral rehydration solution, explaining why the correct amount of, let's say, water, salt, and sugar matters, and connecting these to health practices at home. So in short, application-led approach helps bridge theory and practice. So to further compare these approaches, let us take a look on the different actual science teaching, especially on how a lesson typically begins. So in an inquiry-based approach, the lesson starts with a guiding question or a big question or a phenomenon, such as asking why two plants grow differently under different conditions, prompting investigation and discovery. In a problem based approach, it begins with a real world problem, like let's say clogged canals causing flooding. So the learners analyze the cause and propose solutions. In transdisciplinary approach, the lesson starts with a broad theme or essential question, such as let's say protecting water sources, integrating the ideas across the subjects. In an application led approach, it begins with that task or product, like designing a water filter, where, let's say, learners apply concepts from the start. In STS approach, the lesson starts with a real world issue, such as choosing between coal or renewable energy, and linking science with social and ethical considerations. And with all, while all these support science learning, they differ in their entry point, let's say question, problem, theme, or task or issue, depending on the lesson objective and intended learning experience. So again, while these all support science learning, they can vary, they differ depending on the lesson objective and intended learning experience. Now, to synthesize, this slide shows the relationship between the IDF and the science framework. So, on one hand, the IDF provides the design structure. It helps the alignment of curriculum, teaching, and assessment, and it gives the principles, the aspects, and learning events that make the uh, teaching and learning coherent and intentional. So, in short, it helps us organize the lesson well. On the other hand, you have there the science education framework, which provides the pedagogical grounding. It reminds that science teaching should be rooted in how learners learn science best. So, through inquiry, reasoning, application, and meaningful engagement with real world contexts. It also ensures that our teaching reflects the true nature of science as a discipline. So when we bring these two together, we achieve coherent science instruction. When IDF and the science education framework work together, science instruction becomes more purposeful, connected, and of course, learner centered. Now, as I end this explainer video, I would like to leave you with a challenge. How will you make your science lessons more effective and meaningful for your learners? So, as you go back to your classrooms, the department encourages you to reflect how will your lessons can help learners think, investigate, and make meaning. Or how can you make your lessons aligned, engaging, and connected to real life contexts through the IDF and the science education framework? Because in the end, effective science teaching is not just about what we teach, it is about how learners experience, understand, and apply what they.
This concludes the explainer video for session number 2. Thank you very much. Maraming salamat po sa inyong aktibong pakikinig at pakikilahok sa sesyong ito. Nawa ang mga insights at reflections na inyong nakuha ay magamit ninyo hindi lamang sa mga susunod pa na mga sessions ng training na ito, but also be useful and applicable as you design your science lessons in the classroom. Again, this is Juliven Abreya of the Bureau of Learning Delivery, DepEd Central Office. Thank you and may the force be with you all.